Hi guys, so we are continuing with our look at the SIR model and the foundations of public health. This is a review of the paper that was written by Howard Weiss, and it was published in Materials Mathematics in 2013. And one of the things now that we want to do is mathematical analysis of the model. So if you had done functional analysis or some bit of calculus or real analysis, something like that, that is the kind of focus we are going to be having now. And if you don't like those elements, you need not to worry, because these are the simplified basic forms of elementary analysis, so we don't need to worry. What are we trying to do? Remember, we said our objective is to say our solutions must be bounded. So our solutions must be bounded. All right? So in other words, we don't want solutions that will give us a population of infinity people. We don't want that. Or negative number of people. We don't want that. And now this is also shown through positivity. So we've got positivity of solutions. So let's look at what is happening here. So Howard proceeded and showed that, look, if we look at the right-hand side of equation number 1, so equation number 1 was ds dt is equals to negative beta si, like that. Now, if you focus on the right-hand side, which is this side here, we realize that at all the times, we are seeing that the rate of change, so the rate of change is decreasing. That's what we are seeing here. Right, it's less than 0. So in other words, we see that the SDT is less than or equal to 0. So that is one of the things that he is pointing out in this fact, and that's what we see for equation 1. What about for the equation number 3? Equation number 3 is dr dt. So equation number 3 says dr dt is equals to nu it, like that, because the recovered are coming from the infected compartment, right? The recovering they're coming from the infected compartment, and so it is greater than 0. So this is positive at all the times. So in other words, the RDT is greater than or equal to 0. So that is the first thing that he observes, and he says those things on these two instances. So it's written there and it's written there. But there is something that we know about our population. We are going to say that ST, this is a population, it cannot be negative, so it is greater than or equal to 0. There might be no susceptible people at all, or they can be more. They can be greater than 0. But we must also bear in mind that the total population is n. So in other words, even though ST can be greater than 0, it can only be less than or equal to n. In other words, 0 is less than or equal to ST, less than or equal to n. ST is bounded between 0 and n. And that is a result that we establish here, that we have got there. And also we have got the fact that we have got the initial population, of course, and obviously. So we can also say, look, because ST is the population at any time t. But what is the population that we start with? We start with population S0. So in other words, we can say 0 is less than or equal to initial population less than the population at any time t, but at the end of the day less than n. So that is also accepted, and this is true for R, right? Initial recovered population less than or equal to population at any time t, but also it's less than n. In other words, we cannot have an instance whereby the number of recovered at any time t is greater than the total population, because we are not adding more people to the population. So these is proof of boundedness, to say, look, our solutions are bounded below, they are bounded above. And what then this means is that as time goes to infinity, because these solutions we are talking about, this t that we are talking about, even though it lives in perpetuity, if it keeps on going on and on, such that t goes to infinity, we are going to talk of st, but then when t goes to infinity, this becomes s infinity. And we are simply saying this is equal to the limit as t goes to infinity of st. That's what we have got. And we've got the same situation when time is infinity. It's also for the recovered, it's equal to t as t goes to infinity of rt. What happens? That is the investigation that we've got. But we've already shown that no matter what happens, it's between 0 and n. So this is part of the analysis that is should be being shown by Howard to say, look, we've got long-term limits and they do exist. When we say they exist, it means that they are not going to go to infinity. They are not, it's not unbounded. So we don't have divergence of solutions. So solutions converge. They don't diverge. Okay. Then we have got the second part of the analysis. So this is very, very important, because if you've got divergent solutions, it means that something is wrong with your model, or with your model, and you need to have a relook, because you're dealing with a population of 40 people, and then how come now your solutions are telling us that by the end of the time infinity we will be having infinity or 100 or 2 million or mostly infinity, an infinity number of recovered. It doesn't make sense when your total population, which is constant, is 40. And then we talk about how or when the disease will die out. So the dying out of the disease is the ultimate objective of this modeling business that we do. And what we investigate is, we are interested in how long, all right, so the prevalence of the disease, how long before the disease dies out, which means we are talking about the prevalence of the disease, all right? And to show it without any it was proven here for all initial conditions, even without having a formula for IT. What we then do is that when the disease dies out, it means that as time goes to infinity, the number of infected is 0. Okay? That's what it means. If the disease dies out, the number of infected is 0. Now, we can prove this by contradiction. Suppose it is not 0, or at least we must look for that contradiction, because if it is not 0, we are simply saying that from our equation for the recovered, remember the equation for the recovered, it's here, the r dt, where is the r dt now? The r dt is equals to that, but this is greater than 0. But as t goes to infinity, because we are simply saying greater than 0, so it means that we are going to 1, to 2, to 3, to 4, all the way to infinity. All right? And this is the number of recovered. But we are going to have a problem if our infected population doesn't die out. If this is not decreasing. If this is not decreasing, then it means that R infinity is equals to infinity. It means that as we keep on moving with time going to infinity, the number of recovered is going to be infinite. And that's a problem. That's a problem, but it is already solved because we've discovered that, look, our R is between 0 and n. because that's what it must be. So it will be a contradiction if it happens then that it goes to infinity. I hope that this makes a lot of sense to you. You need to have some intuitive understanding of what is going on here, but it is pretty much straightforward as it is given to you. That look, we know that this guy, the RDT is greater than 0, yes, but if it happens that this guy, I infinity, as we go to infinity, I is growing, then we are going to have a situation whereby R, which is dependent on I, is also going to keep on going to infinity, and that's a problem. So that's why we say, look, there is a contradiction, because we've discovered already that R is bounded between 0 and n. Okay,